Hello everybody, thank you for tuning in and looking at our lecture online instead of in the classroom. I'll try to go fast, but we'll see how it goes. It's the first time I'm recording the video, but I wanted to learn it. It's some very useful tools in teaching. So we'll start with chapter 17, electric forces and fields. And let's just think for a minute, what our life be without electricity? It's not going to be fun, right? Just think the snowstorm that was on Monday and you lost your power, and oh my gosh, you would be miserable. No heat, no light, no TV, no internet, no microwave, hard to make food. It just everywhere. Electricity is everywhere. We need it in our everyday life. You can't even imagine how important it is in our life. As soon as, well, when we have it, we don't notice it. When we don't have it, we're pretty miserable. So, but it's also a very hard topic to study, but I think it's a very fun topic to teach. I really like it. It's lots of magic involved with it, and there's so many demonstrations I hope I'll be able to do in the class with you later. So, but right now, in nature, where electricity occurs, right? I have this picture for you. This one, right? Look, you can circle it. A lightning storm, right? We've seen lightning. People in 100,000 years ago saw the lightning. They didn't know what it was, but it has a name right now. It's electrical discharge in atmosphere. So you can also experience similar discharge if you walk in a dry weather in the carpet and then you touch metal knob or something metal, you'll feel electrical shock. That's not really pleasant, but that's where you experience electricity, and that's how you can see it exist and feel what it is. So let's go to the next slide. Discovery of electricity is generally credited to Greeks, and it happened approximately 2,500 years ago. And there's another phenomena that they've noticed that also has electrical nature. And if you use amber, it's a type of tree sap. When it's dried, it becomes little beautiful or orange yellow stone that's used in jewelry or in some other applications. So if you take this piece of amber, that's what they did, and you rub it with an animal fur, the amber can attract small pieces of dust. So what's happening? If dust get attracted to amber, it means there's something pulling it or pushing it toward amber. That means there is a force, right? Forces push or pull. And the nature of this force been contributed to electricity, and it's called electric force. As far as Greek word for amber was electron, that's where the name electricity and electrons came from. And this is a basic historical reference how electricity was discovered and what was in the beginning when scientists, physicists started learning about electricity and figuring out if we can use it in everyday life. So right now, it's a modern experiment, and I'll try to introduce it on Thursday to show you in class. If we would take a plastic rod, or if you have a plastic comb in your household, or a plastic pen, then grab your cat or a dog or little brother or sister and rub it on the fur or hair. And then if you have little tiny pieces of paper, like on this picture, see those little tiny pieces of paper, you can they're going to get attracted to this rod. And this is how you can see that this force is actually real. So there is something exists there that pulls the pieces of paper towards the rod. You don't feel it. If you put your hand there, you're not going to feel anything, but paper does. So something is happening. Let's go to the next slide. So basic properties of charges. You probably know it from chemistry or just from it's a general knowledge. You definitely had it in your middle school physical sciences. So that should sound familiar. We'll just summarize it fast. There are two types of electric charges, right? Positive and negative. Protons, this is a part of an atom, have positive charges, and electrons have negative charges. What's important to know is that this is the minimum possible charge. Protons and electrons, they carry the same amount of charge, 1.6 10 to the negative 19 coulomb. This is the unit. This is just a number. And there is no way you can have a charge smaller than that. So every positive charge or every negative charge that object can carry is consist of an integer number of electrons or protons. So there is no electrical charge smaller than 1.6 10 to the negative 19 coulomb. So charge is quantized. It's just like marbles. And assume you never can split the marble. That's just how it is. Sorry, I have a cold, so you're going to hear my voice. Basic properties of charges. Again, hopefully you remember it. Like charges repel. If you have a positive charge and positive charge next to each other, so you're going to repel, because they don't want to be next to each other. If you have two negative charges next to each other, they also repel. They don't want to be next to each other. This is like an example where similar like charges repel, and opposites are going to be opposites attract. So this is another example. So you have positive charge next to negative charge, and negative charge next to positive charge. So you're going to experience attraction force. They want to be next to each other. So this is important quality. Also, charge is conserved. It doesn't go anywhere. It just is. The total charge on an object is the sum of all individual charges carried by the object. So if we have a certain number of positive charge and the same number of negative charge, they're going to cancel each other out, and there is no charge in the object. But the total charge is just the sum of everything, all individual charges carried by the object. Charge can move from place to place and from one object to another, but the total charge of the universe does not change. So in a very fancy way, when the charges are being actually created in the particle physics, very high energy situations, a photon can strike an atom, and you'll have electron and positron created, but it's going to be always happening in pairs. So positive and negative charge created in pairs. So the total charge of the universe does not change. Again, stays the same. What is electric charge? An actual definition is not possible. It's just a fundamental property of matter. Like, we have mass, we have certain sizes, we tall, we small, so it's just something that matter has. It's one of the fundamental properties. To measure charge in standard system of units, we use coulombs. This is in honor of Charles de Coulomb, physicist who did lots of work with electricity a long time ago. Symbols that are going to be used are E, little e. This is when we have to denote the magnitude of the charge on the electron or proton, or little q and capital Q used to denote charge in general. Let's solve problem 4 from a textbook. Approximately how many electrons are in your body? What is the total charge of these electrons? To solve this problem, we only can estimate it. We cannot calculate it exactly. But the first we need to know, take something for human body. On average, total mass of a person is about 17 kilograms. And we need to know some facts from chemistry about how many electrons would be in a human body. To calculate it, we need to know molecular mass of water. Molecular mass of water using periodic table is 18 gram per mole. Pay attention to the units. Don't confuse kilograms and grams. Knowing those two facts, we can calculate number of moles in the human body. I also assumed that what a human body basically consists of water. So this is how many moles of water in the human body. The number of molecules in the water then can be in the human body can be found out as multiplication little n times Avogadro number. We need another fact of information: how many electrons in each water molecule. And because it is H2O, we have 10 electrons, 2 for hydrogen and 8 for oxygen. So 10 electrons total. That's pretty much it. That's all we need to know. So let's now calculate N of electrons in a human body. Then it's going to be equal M of a human body divided by molecular mass of water multiplied by Avogadro number multiplied by 10. Plug in all the numbers and going from kilograms to grams, or opposite way, we can calculate that number of electrons, this is electrons, is going to be 2.34 times 10 to the 28 power. So hence, knowing charge of 1 electron, we can calculate total charge of electrons in the human body as negative 1/6 10 to the negative 19th multiplied by this number we just calculated, this one, and the answer is going to be negative 374. So it's 3.74 times 10 to the 9th power. And this is coulombs, measured in coulombs. So that's your answer. Let's solve problem 8 from a text. The charge per unit length on a glass rod is lambda. If the rod is 2.5 meters long, how many excess electrons are on the rod? So we need to understand what is charge per unit length first. And this is exactly what it is. Lambda is charge per unit length. So then total charge on a rod is lambda times L. Plug in values. Negative 7.5, 10 to the minus 6 for micro, multiplied by 2.5, and the final answer is negative 1.86 times 10 to the negative 5, so this is 5. And they also ask us how many excess electrons are on the rod. So number of electrons, excess electrons, not the total number, is we have to divide this total charge, 1.86 10 to the negative 5, divided by electron charge, 1.6 10 to the negative 19. There's minus sign here, so but they cancel out, so the answer is 1.2 10 to the 14 electrons.